Okay, so this is a simple barometer setup. This is how people first started measuring changes in temperature and the weather. And so you have this upside down, I forget what those are called, flasks. You then fill up this flask fully and put it in a dish like this. The water is going to fall down a little bit, but it's going to be held by the vacuum there. And so you have this pressure of air pushing the water up into the flask, but you also have the weight of gravity on the water pulling it down. And what they would do then is they would measure the height of this to figure out exactly what the temperature change would be. And so we start with pressure equals P0 plus rho GH. And so rho is the density. This P0 is actually the pressure of the atmosphere. That's the initial pressure that the system is feeling. And then this P, we just call it 0 because the pressure inside of the vial is 0. And so if you subtract the pressure of the atmosphere over, what you're looking at basically is you're setting the pressure of gravity equal with the pressure of the atmosphere pushing your water back up the tube. And so you may be wondering, where is the negative? Well, we just understand that they are working against each other, and so if you set them equal to each other, you shouldn't have to have that negative. All right, so the pressure of the atmosphere, if we take that and just get our height alone here, we can actually estimate how big that tube has to be. If we know the pressure, the density, and gravity, we can figure out how tall would this instrument have to be so that we can actually see that change. And so if we do this, the pressure of the atmosphere is 1.01 times 10 to the 5th. The density of water is 1,000. And then gravity is 9.8. Now you crunch this out on your calculator, you get 10.3 meters, which the book rounds it to be about 10 meters. And so the idea here is that if you wanted to construct one of these and just use water as your liquid, you would have to build a tube that's 10 meters tall to see and measure the changes in the atmosphere. So this obviously doesn't work very well to have a 30-foot tall flask. And so what people did instead was they used a different liquid. So that's example number 2. You should try this. Imagine that we used mercury. So we are going to now use mercury as our liquid, and the rho for mercury is 13,000 kilograms per meters cubed. So the density is much higher, which means that you're going to have a much smaller instrument. So you should pause the video and you should try to figure out how tall would this have to be if you're using mercury instead. Okay, so we're going to go through this. We're going to have the same kind of setup. The atmosphere pushing the mercury back up into the tube because of the vacuum is going to be the same as the gravity of the mercury pulling down inside the tube. So the pressure of the atmosphere divided by rho g will give our height. And so here's what we calculate. 1.01 times 10 to the 5th, all divided by 13,000 times 9.8. Okay. So we throw this in our calculator. Okay, I'm getting 0.792. So with sig figs, you're going to be around 0.79 meters. Okay, so it's a lot easier to be using a meter tall measure than to do a 30-foot tall measure. So that's why they used mercury in the very beginning of these kind of measurements. So this also leads us to one interesting fact. So we have water reservoirs and we use these wells to get water up to our houses. Here's the issue though. You could think of it 2 ways. You could have a water pump at the top that's pulling water out by creating a vacuum, or you could have a pump underneath next to the well pushing the water up the tube. Okay, now we just learned that in our first example, if you have water, the vacuum will hold the water up 30 feet tall, or about 10 meters. So the interesting thing about this is if you had a pump up at the top pulling water out, even if there's zero pressure, you're going to have a hard time getting anything that's below 10 meters below the surface. But if you have a pump under here, you can be exerting positive pressure, pushing the water up to the surface. And I don't know if there's a limit on if you have the pump housed underwater. So here, you have a very practical application. If you want to be pumping water, you need to house the pump underneath if you're going to go below 10 meters.